So when we're doing a ligand binding study on a protein that we don't know much about, we might try to figure out what is the ligand for a protein and what is not a ligand. And in order to do that quantitatively, we have to have some mathematical expressions so that we can do this type of work. And so we might use a term which is called the dissociation constant, for instance, which is a big K, capital letter K, D. So this is called dissociation constant. So what that actually is it's just an equilibrium constant. So if we have an equilibrium between protein and a ligand to form a protein-ligand complex, we might write as the equilibrium constant, we'd say K, for instance, KEQ equals the law of mass action. So at equilibrium, that would be the concentration of PL at equilibrium over the concentration of P at equilibrium and the concentration of the ligand at equilibrium. Okay, and so that's something that we've seen since chapter 1, topic 1, right, in thermodynamics. All right. So another way to express this when we're talking about ligand binding is as Ka. And so we call this the equilibrium association constant. Now, it's really simple to go from here, where if we have Ka, whoops, sorry, forgot the A, Ka to Kd, because Ka is simply equal to 1 over Kd. Okay? And so what we're really just looking at is we're looking at equilibrium constants here. And from that we can determine, for instance, if something has a Kd that is relatively low, like for instance, if for this triangle possible ligand, if we have a Kd that's equal to 10 micromolar versus this compound called not a ligand has a Kd of 100 millimolar, then we can compare the two. And what's nice about working in Kd to look at ligand affinity is that the smaller the number that we have, the more tightly it binds to the protein. So a Kd of 10 micromolar is much smaller than a Kd of 100 micromolar. In fact, it's 10,000 times smaller. So this binds with a 10,000-fold greater affinity than something with a Kd of 100 millimolar.